In this video we will be deriving equations for simple harmonic motion, or SHM. Let's first look at the general condition for SHM. For SHM to occur, the displacement of the object must be directly proportional to the negative of its acceleration. Let's have a guess at an equation for the displacement of an object undergoing SHM. As we know we have periodic motion, perhaps a sine wave is a good idea to try. So if we have a particle moving with an amplitude of a, and an angular frequency of omega, our displacement at time t will be a sine omega t. Velocity is the rate of change of displacement, so if we differentiate an equation for displacement, we will get an equation for velocity. Using chain rule, we differentiate the inside of the equation first, so this gives us an omega term. If we then differentiate the outside, we get cosine, giving us a formula for velocity, v equals a omega cosine omega t. If we continue our differentiation, we get an equation for acceleration. Again using the chain rule, we differentiate the inside first, giving us another omega term. Then differentiating the outside, we get negative sine, giving us a formula for acceleration, a equals negative a omega squared sine omega t. Now if we look back at our original equation for displacement, we can substitute this into our equation for acceleration. This gives us a final equation for acceleration, a equals negative c times x, where c is omega squared. Now let's look at an example of SHM in practice, the simple pendulum, a heavy weight on a length of light, inextensible string. If we look at the forces acting on our pendulum, the weight of pendulum creates a downwards force, the vertical component of which is opposed by the tension. So the tension in the string equals mg cos theta. This also creates a restoring force back towards the equilibrium point. This restoring force is mg sin theta. Now let's define some distances on our pendulum. The length of our pendulum is measured from the pivot to the center of mass, here the center of our pendulum bob. The displacement of our pendulum is measured from the equilibrium point to the center of mass again. For convenience later we are going to define this displacement as a negative value, as it is in the opposite direction to the force we have already defined. Now let's use these forces and displacements to derive an equation for the time period of a pendulum. We have our equation for restoring force, F equals mg sin theta. We are now going to use the small angle approximation, which states that for small angles, sin theta is approximately equal to theta, to simplify our equation. So we can substitute this into our equation for force, giving us F equals mg theta. As our pendulum swings, the bob traces out an arc. The length of this arc is equal to the radius L, times the angle theta in radians. So we can rearrange this to give us theta equals x over L. We can now substitute this into our equation for force, giving us F equals mgx over L. Let's clear some old equations up and now look back at our definition for SHM, x equals negative omega squared a, where is the acceleration. Applying Newton's second law, a equals F over m, we can substitute this into our equation for displacement, giving us x equals negative omega squared F over m. Now we have two equations for force, so we can set them equal to each other. Rearranging this equation to make omega the subject, we get 1 over omega squared equals g over L. Now we can substitute omega equals 2 pi over t, and rearrange to get our final equation for the time period of a simple pendulum, t equals 2 pi root L over g. Now let's look at a second example of SHM in practice, a mass attached to a spring. If we displace the mass beyond the equilibrium point and let it go, it will oscillate up and down around this point. In a real example, the oscillations decrease in amplitude over time due to damping forces. However, for our ideal example, we can ignore these. Let's stretch and hold our spring and look at the forces involved. We have weight acting downwards equal to mg and the spring force equal to spring constant, k times the displacement, labeled x here. The natural length is the length of our spring if it is unstretched. It is from this length that we measure all the extensions. The equilibrium position is where these forces would be balanced and the resultant force would be zero. Okay, let's start with the derivation. The force on a spring is equal to the spring constant times the extension. At the equilibrium position, the forces are balanced, so weight minus the spring constant would equal 0, so the weight is equal to K times the extension the weight causes, X in this setup. Now if we look at the forces in our extra stretched position. Here the weight is the same but the spring force now is increased, as the extension has, so the resultant force F now equals mg, K, x plus y. If we expand our brackets, we get that the resultant force equals mass times g minus kx minus chi. Earlier we established that kx equals mg, so they cancel out leaving us with F equals minus ky. Right now let's tidy up. Let's look at the SHM side of things. Applying our condition for SHM, we get that y equals minus omega squared a. Again we apply Newton's second law and sub this in to get force equals minus my divided by omega squared. Again a quick tidy. As we have two formulas for the same force, we can make them equal to each other. Now we can cancel to get 1 over omega squared equals k over m. Finally we can substitute our definition for omega in, to get our final formula for a spring in SHM, T equals 2 pi times the square root of m over k. So in summary we have shown that x equals a sin omega t is a valid equation for an object in SHM. We used the condition for SHM, displacement is proportional to negative acceleration to derive two formulas. For a pendulum, period equals 2 pi times the square root of length over g. And for a spring, period equals 2 pi times the square root of the mass divided by the spring constant. The methodology used here is applicable for any system in SHM. Look for the forces involved, try to get a formula where force is proportional to negative displacement, before applying the condition for SHM to get a final formula. Hope this all helps and thanks for watching.